Okay, hey everybody. Excuse me. Welcome back to chapter 1. Yesterday we did section 1 point, or last class I should say, we did section 1.4, where we looked at some reactions of uh, organic compounds, or reactions involved in organic synthesis, I should say. So today will be a very kind of quick little class. We'll do section 1.5, the structure of polymers. We'll kind of talk about how they're classified, what makes up polymers, and different kind of classification structures of them. So we'll define polymer, monomer, repeating unit, talk about some examples, and then talk about different types or classifications of polymers. Homo, co, linear, branch, network, cross. We'll look at cross-linking, things like that. It's pretty straightforward, mostly a studying terms type of unit. You should definitely know all these different types of terms, but it's a lot easier than it looks. I mean, the names: homopolymer, copolymer, linear polymer, branch, they're exactly, when you break the words or terminology down, it's exactly what it sounds like. So it might look a little intimidating, but this is a pretty straightforward section. So we won't get into history in this course at all, but every once in a while I'll kind of give you some background information. I know in the thermochemistry unit we'll talk a little bit about when it was kind of first looked at. For polymers in 1827, so 1830, we'll say, this word polymer was coined. Okay, polymer would come from Greek poly, meaning many, like a polygon has many different sides, I guess, and then mer, meaning parts. It comes from the term meros, so polymer, many parts. And this word was used to denote molecular substances with high molecular weight. So remember, back in 1120, typically something with high molecular weight, has atoms in it that have large molecular weights as well. Well, if we're talking about polymers made from carbon and hydrogen, and even oxygen and nitrogen functional groups, on the periodic table, none of those actually have very large molecular weights compared to some of the heavy metals. So when you have a polymer that has a large molecular weight, it's typically because it's a large, long carbon chain, like extraordinarily long, very complex compound or molecule. And we'll talk a little bit more about that later in this chapter when we talk about the properties and intermolecular forces. I mean, this isn't kind of like things we looked at in 1120, like if you remember Lewis dot diagrams in 1120, like CO2 and NH3. I mean, we're talking hundreds of carbons possibly in these chains. So what's important to note from this is that polymers are made up of repeating units called monomers. Now, mono from Greek, and you guys learned Greek prefixes in 1120, mono means one. So a polymer is many parts made up of monomers, or one part. So you can think of like Legos or building blocks, and you just keep adding them and stacking them. Stacking cups, for example, just stack, laying them end to end and keep on building and building and building. These little units or building blocks are called monomers, and then they make a bigger compound called a polymer. And polymers can be synthetic. And when you hear the word synthetic, it means, human made, not natural. Things like polystyrene. So styrofoam, there's like PVC, polyvinyl chloride is another polymer, polyethylene, nylon. I mean, there's so many synthetic polymers. And then there's natural polymers. So like DNA, the DNA in your body and the proteins in your body are made up of these building blocks that repeated units. I don't know if you guys have done much biology. I haven't done it in many years, but like the building blocks of DNA, so the nucleotides, what is it? Adenine, cytosine, guanine, and thymine, if you remember those terms. I barely remember them from university. I haven't taught biology before, but these are repeating units that form DNA. So you can have natural polymers or synthetic, meaning again, human created. So a monomer is a mono meaning one, mer meaning part, is a molecule that may bind chemically to other polymers. So they can be fairly reactive. They might need special conditions to react. So maybe heat, maybe light, maybe an acid, maybe a base or something to help them react. But they are typically fairly reactive, and they can bind chemically to other molecules, typically other monomers, to form a polymer. And that process of creating a polymer is called polymerization. Polymerization, kind of a big word, but it's the process of linking monomer units together, these building blocks together to form a larger compound. So this is kind of getting into the first part of your definitions. This section 1.5 is basically comprised of many definitions, and they're a lot easier than they sound. So the first would have been, polymer stands for many parts, large molecule, large molecular weight made from monomers. And again, monomer is a chemical or a molecule, small molecule that can bind together to others to form a polymer. Well, polymers can contain kind of different types of classifications, or they can be classified differently. Polymers that have only one type of repeating unit, so the same block over and over and over and over, would be a homopolymer. So think of like a homogeneous solution. Like the word homo kind of means like it's the same thing. So homogeneous looks like the same mixture. I don't know if you remember that from chemistry 1120, but a homogeneous solution, the whole solution looks the same. Salt water would be a good example of that. It just looks like water, but it actually has things in it. A homopolymer is a polymer made up of the same block over and over. So what about a copolymer? Well, think of the word co as in like cooperation, collaboration. When you collaborate or cooperate with people, it's normally you working with other people. So a copolymer is made up of a mixture of repeating units. So homo are the same units over and over. Copolymers are mixtures. It could be 2 units repeating. It could have 3 or 4 more units. I mean, it can get really complicated. But homopolymers just have 1, copolymers, 2 or more. Polystyrene is a good example of a homopolymer. It's just this styrene monomer is reacted over and over and over and over to form polystyrene. Ethyl vinyl acetate contains more than one variety of repeating unit. I have some examples of this here. I'll show you in a minute, but ethyl vinyl acetate would be a little bit more complicated. It has, 2 or more than one variety of repeating unit. So they call it a copolymer. So here's an example. And again, you're not going to have to draw this. Don't worry. You need to know how to classify what a homopolymer is. So this is my monomer. I have one monomer, one building block that gets repeated over and over. And what happens is this double bond is kind of like the active site where we're seeing this chemical reaction happen. The ethene part of this, or the alkene part of this, I should say. You'll learn, any of you going on to chemistry 2420, that the aromatic ring is pretty stable, pretty unreactive, but an alkene is much more reactive. So under certain conditions, we can get that double bond to break. And I have an example, maybe a more detailed picture of this later in this course, but the double bond kind of breaks and attaches to another monomer, and his double bond breaks. They form an alkane. So you'll notice, like, instead of a double bond here, it's all single bonds. I don't know if you can see me, like I'm kind of just scribbling down here, but it's all single bonds because those double bonds are the active site where we're getting the linking to happen. But it's the same unit over and over and over and over and over. The same building block, the same Lego piece, just over and over and over. This is a homopolymer. Now, when you have two reactants, A and B coming together, this cannot be a homopolymer. The fact that there's two of them means we're getting a copolymer. Okay, so in this part, we're getting multiple building blocks, right? You have kind of like the styrene molecule here separated. So we have like building blocks, building blocks, building blocks, building block. It's, alternating A, B, A, B, A, B, and it will do that forever and ever and ever. Well, not forever, but the order, the pattern will stay the same. So A, B, A, B, A, B. This is styrene butadiene. So we have butadiene and styrene mixing together to form a copolymer. Okay, so polymers during the past 7 years. So it's pretty recent. I mean, especially the discovery of oil is when we really took off. Well, after the discovery of oil, it really took off because a lot of our polymers are made through natural gas or petroleum-based chemicals. So chemists have learned in the last 70 years, maybe 80 years, I made these slides a while ago, to form synthetic polymers, in the lab by taking monomers through controlled chemical reactions. So this is organic synthesis. Most synthetic polymers, or at least many of them, have a carbon-carbon backbone. Okay, they're carbon chains, but when I say backbone, there could be things sticking off of the chain. There's more than just a carbon chain. They can get very complicated. Carbon, and again, you'll learn more about this if you do get into hydrocarbon chemistry, but I mean, carbon is an amazing molecule, like so awesome. It's it has such an exceptional ability to form so many strong and stable bonds in so many different combinations, alkanes, alkenes, alkynes, there's rings, there's aromatic rings. It's crazy. It's like the ultimate building block, which is why organic life is so diverse. Living things are made up of carbon, but no two things are even remotely the same. So, I mean, it's incredible. We could talk about it for a long time, but I won't get into it. So you can classify, and when I say classify, it's like identifying something. You think about SUVs. There's Toyota brand. There's Mercedes. There's, I don't know, I'm not a car guy. Nissan. That would be a classification of an SUV. Or we could kind of change it around. We could say, what are classifications of motor vehicles? So you could have a car, a hybrid, or a SUV, a truck. There's so many different types of ways to classify something. So polymers can be classified also in many different ways, not just one grouping can classify them all. You can look at how they react, how the molecules grow, macromolecule meaning the big molecule. You can classify them by their structure or their chemical properties. So I have a pretty intimidating looking slide here, but it's really not that hard. You do not have to memorize this, don't worry, but we are going to look at some of these things in the remainder of this unit. We're going to look at, what are polymers that are formed by addition or condensation? What do they look like? We'll look at linear, branched, and cross-linked actually today. And then towards the end of this chapter, we'll look at what a thermoplastic is and what a thermoset polymer is. So we'll look at most of this, but like some of these, not necessarily. Latter, we may kind of look at when we talk about cross-linking, but we'll just kind of have a brief overview of these types of polymers. And I think we're going to start with the structure. I think that's what today's lecture is about. Yeah. So linear polymers. Now, I'm going to throw some terms at you very quickly because this is pretty straightforward. We're going to look at linear, branched, cross-linked, and network. And it's way, way, way easier than it sounds. Well, it's the way it sounds is exactly what it is. A linear polymer is a straight chain polymer. It's in a line. Now, when I say a line, remember the way that the bond angles work for alkanes. That there's angles in here, but It's just one long chain. There's no branches. There's nothing too crazy here. It's just whoosh, one long chain. You can kind of see here the term is misleading because the geometry means the tetrahedral shape of a carbon atom means the chain isn't necessarily straight, but you'll see what I mean when I get into branched. The difference between linear and branched makes this a lot easier. So as the polymer chain grows, this is where linear polymers get kind of interesting. As it gets longer and longer and longer, it can begin to fold back on itself in random ways. And these linear molecules, they're not so bulky because there's no branches, there's nothing sticking off. Like, think of folding a sheet of paper. It's not a bulky thing. When you fold a sheet of paper, it goes flat again, and then you fold it again and it's still flat, and you fold it over and over, and the density gets higher and higher and higher. So some linear polymers can create very tightly packed, almost crystalline structures. And in your engineering program, you might hear about HDPE, or high density polyethylene. That's a product of this polymer. So it's ethylene molecules, or ethene molecules, form a long carbon chain, a big alkane basically, but they can fold over on themselves and create this high density polymer, very rigid kind of structure. See, and I mean, I just kind of want to detour here. Like, polymers are amazing because some of them are like very rigid, meaning like if under stress they'll crack. Some of them are like rubber, where you can stretch them and bend them, like think of a car tire. And think of what's another piece of plastic you might like? Okay, think of a plastic fork from a restaurant, and think of the tire on your car or vehicle. Yeah, we say car in Canada a lot. For a car could mean anything, but think about that, right? A rubber tire and a plastic fork from a restaurant. They're both polymers, but they're not even close to being similar in chemical properties, sorry, I should even say physical properties. If you put any pressure or stress on a plastic fork, it immediately shatters, whereas a rubber tire it's flexible, it bends, it stretches. All right, branch polymers. What's a branch polymer? Well, you don't see a lot of branched trees around the Middle East here, or well, certainly not in Doha or Qatar. But when I think of branched, I always think of like, a tree. So you have a tree, and a tree has many, many, many branches, right, sticking up out of it. And that's kind of where the term branch polymer comes from. I would assume a branch is kind of like a detour off a main road, you could say. So if I had like, a polymer, and I'll just very, very crudely draw this. The minute I start putting in branches, sorry, my pen is going a little wild here, but the minute you have side chains, you could call it, off of the main chain, that's where the name branch comes from. So, this this isn't as easily packable as a linear polymer. I said linear is like folding over a piece of paper, and you get very tightly packed structure. Well, imagine trying to fold this object over on itself. All of these branches are going to get in the way, and they're going to create gaps or space. So this is kind of like folding over bubble wrap, or like folding over a pillow. And now I know a pillow, you don't think of branches, but like, all these branches create space and gaps, and this creates a low density situation. So a branch polymer folding around on itself would make a low density LDPE, low density polyethylene. Kind of interesting. So you can see here, this is a pretty crazy looking, but it is a branched polymer. There is kind of like a central thing happening here, but there's branches everywhere. Lots of space, very more complicated molecules. The amount of this branching affects intermolecular forces, which therefore affects physical properties. We'll talk more about intermolecular forces at the end of this unit, but intermolecular forces, the shapes of these polymers, can change things such as viscosity and elasticity. Elasticity is kind of like how well it stretches. Viscosity is its resistance to flow, and you can think of that like thickness. A good example of something that's viscous is honey, and something that's not as viscous would be like water. Viscous is, or sorry, honey is very viscous, very thick. So if I try to pour it, it's very slow moving, whereas water pours much more readily. So branches prevent chains from getting too close to each other for intermolecular forces to work quite as effectively. So that kind of changes its properties. And I can't like give you, I can't give you like exact properties of a branch polymer because there's hundreds of thousands of polymers. They're all different. You kind of have to look at each polymer as its own entity when you're looking at the physical properties. Okay, so what's a cross-linked polymer? Well, this is exactly what it sounds like, or at least what I think it sounds like. It's a polymer where there's linkings that cross the well, I'll say the carbon chain or cross the molecule. There was an example previous. It said like here, ladder. You can see the word ladder. You can kind of think of a ladder like a cross linkage. You have like the two vertical parts of the ladder. Did I skip too far? No. And then you have the rungs, where you'd put your feet. These would be the cross linkages. I think in your first lab, you kind of create cross linkages to make rubber from borax and glue. So you'll make a cross-link polymer in the lab, in your first lab. And the cross-linking takes glue and borax from, a kind of two liquids. Glue is a little viscous, but borax is a liquid, or a very low viscosity liquid. You mix them together and you get literally like a rubber ball because of the cross-linking of these polymers. Pretty cool. So cross links between polymer chains can make the polymer more elastic. So, like lab one. The cross-linking can also help just decrease the viscosity, the resistance of flow. But in lab one, you'll see this part in action. Lab one is pretty cool. So an example of a cross-link polymer, and again, you can see how this looks like a ladder, is vulcanized rubber, or the rubber on like your car tire, vehicle tire. It's made by sulfur atoms. They don't have to be sulfur atoms, but in this case they are. Okay, so it kind of looks like a ladder in this situation. Very tough, very flexible, and the cross-linking is what keeps it flexible, keeps it from breaking. The cross-linking is providing kind of like a structural integrity to this that allows it to flex. And the last one is a network polymer. Now, network, think of a computer network. It has so many different parts. So, the wires are connecting hundreds and thousands of computers. Like think of the internet, right, as a network, or even the network at the college campus. There's, between the wireless and wired connections and phone lines, it's going everywhere. You can almost think of this like a spider web, incredibly complex. So a network polymer is highly branched, many cross linkings, there's many interconnections between these, and it's so highly interconnected and so complex, and so much going on, so much linking going on. You get a chemical, this is just an example of it, called bakelite. Bakelite is very brittle. It's crystalline almost in its structure. It's so kind of well networked that it becomes almost like, well, it becomes a solid, and it's very, very, very strong solid. I don't know that bakelite is used a whole lot in modern times, but if you kind of Google bakelite, you can see pictures of it. In its kind of rawest form, it looks almost like a crystal, like a gem. But anyways, that's just an example of that. Okay, so that's it for me here, guys. Thank you very much for today. We'll get started in the next class with more different types of polymers, but that's it for us today. All right, thanks everybody. Have a great day.